All right. Oh, we have a clap. The thing is going. Yes, yes. I know. A wee bit late. These things happen. All I know is if you like or have something to say about this, feel free to let us know below. But as of today, what are we going to be talking about? So since we're going into this thing right here, I give my casual, slightly new attempt to shill in there without telling people to. Well, I hate being told what to do. That's one of those things. You give people options. Maybe that's why I always like those choose your own adventures. And apparently, this is plaster, so I can probably actually throw a couple more screws in there and not worry too much. Just don't hit the outlets. That's how it works. All right. So today we're going to be talking about the Leech Lattice. Why? Because Thad gave me a call earlier and sent me a very interesting thing. I checked, trust, verified, and it's very interesting. We're going to get into it. All right, so I'm just going to write this here on the board. So we're going to be talking about the Leech Lattice. What is that? Well, apparently, the Leech Lattice is, I'm not going to say that some mathematicians and physicists salivate over it. I can only speak for myself. I might be salivating a little bit. But essentially what it is a 24-dimensional lattice structure that apparently, I think if you get a double covered or something, you end up, it seems to explain a lot of things within the physical world. So we're going to let some folks join from wherever you may come from, whether it's on the YouTubes, on the X Twitters, on the blue skies, or wherever on the internet, the Discords, or just because the algorithm for some reason thought it maybe should bring you here. You're a math student, you're going along, you're looking into these cool lattice structures and everything, and all of a sudden it's like, what's this crazy dude with a red bandana doing here? Okay. So rather than do that, a lot of stuff is in the doobly-doo below. So let's just get into it so I can learn with you all. Because we're in this together, we're together forever. I believe there's an ooh yeah in there somewhere. All right. So let's do this. How to construct the Leech Lattice. So this was brought to us by, it looks like Richard E Borcherds. I believe he's a former Fields Medal winner there. So what's the Fields Medal? It's basically like the Nobel Prize for math. Why is there no Nobel Prize for mathematics? Because according to the deep lore, Alfred Nobel's wife had an affair with the best mathematician of the time, and he knew he would end up winning it at some point. So that's the deep lore that we had there. Okay. So what the heck is the Leech Lattice? Okay. So what this is 9 minutes, and this is totally for educational use. I don't think Richard Borcherds will strike. I could be wrong. Let's get into it. There's Mr. Borcherds right there.
This talk will be about the Leech Lattice, or more precisely, about a very short construction of the Leech Lattice found by John Conway and Neil Sloan.
Oh, John Conway. That seems to be a very notable dude. Oh, Sloan. I feel like we've named a bunch of things in math after. Okay, well, again, actually, Neil Sloan. Neil Sloan. Neil Sloan is an American mathematician. Going to our friends at Wikipedia. I know I'm not showing the tab here, but there we go. His major contribution to the field of math combinatorics, error correcting codes, and sphere packing. Well, I guess the Leech Lattice is one of the best things for that. So let's continue with Mr. Borcherds.
So the first problem is, what is the Leech Lattice? And for that matter, what is a lattice?
Okay, now number one, this is, I believe, okay, so I think that's the 120 cell, just because I've seen it. It also has like a pentagonal thing, so it reminds me of a dodecahedron. So it's basically a hyperdodecahedron there. That's not the Leech Lattice. We'll get into it.
A lattice, we recall, just means a regular arrangement of points. So for example, in 2 dimensions, we could have a square lattice, like the points on the vertices of a chessboard, and go on forever. Another lattice in 2 dimensions would be a triangular lattice, where you arrange them at the vertices of an equilateral triangle, and there are lots of other 2-dimensional lattices.
Coincidentally, the triangle and the square technically the simplex and one whatever the n-dimensional cube, aka your square in 2 dimensions and everything. Those are the only 2 tilings that I believe tessellate all dimensional planes. Coincidentally, once you get above 4, which 4 dimensions has countably infinite, apparently, number of tilings, once you get past that, 5 and up, it's all just these 2. I think that's kind of neat.
A good way of thinking of a lattice is you can think of it as being a packing of spheres. So you can think of these points as being the centers of spheres. So here the spheres would look like this. I'm calling them spheres. You may say they're circles, not spheres, but a circle is a sphere in 2 dimensions, and more generally I want to talk about lattices in various other dimensions.
Well, that's why sometimes you hear the term the n-dimensional sphere. Well, this is the n-dimensional sphere in 2 dimensions. Why? Because it's flat. We don't have other degrees and directions we can go. I don't know, apparently at higher dimensions, things get easier to move around. It's in 3, we can start to get knotted and stuff. And all types of crazy stuff happens here where we live, apparently. Especially if you add in +1.
And here, the spheres or possibly circles will kind of look like this, and so on. So these are packings in 2 dimensions. In 3 dimensions, you could think of a lattice as being something like the centers of the atoms in a crystal, and the spheres might be the sort of solid atoms touching each other. It turns out that lattices are very special in 8 and 24 dimensions.
Oh, because at the right dimensional magnitudes, cool stuff happens. Let's see what happens. All right.
Which is very weird. In fact, this wasn't really noticed until relatively recently. I mean, people spent 100 or 200 years studying lattices without noticing that these 2 dimensions were very special. Why are these dimensions so special? I don't know, and I don't think anybody else does either. Maybe.
I love the honesty. I love it. Why are these 2 dimensions special? I don't know, and I don't think anybody does. When you have a brilliant person, especially if they happen to have a lot of accomplishments, I tend to find there's a correlation with them when you present them with something. They're like, I don't know. Why? Because that's an honest answer. Why do they have to lie? You don't got to pretend you're smart. There's a lot of folks are already like, oh, yeah, you're a really smart dude. You want all these things. So continue, Mr. Borcherds.
It's sort of a practical joke played on us by the universe. In particular, in 8 and 24 dimensions, there are 2 very special lattices. In 8 dimensions, it's called E8 for complicated historical reasons. And in 24 dimensions, it's called the Leech Lattice because it was discovered by John Leech in the early 1960s.
Wait a second. E8? That's one of our friends. I think that's Garrett Lacey's thing that he's looking at. He's like, well, you have this exceptional Lie group of 8 of the 8th dimension. Why? Because it can do all these things, and it seems to replicate a lot of the things and the spin groups and the geometries of particle physics. And after you get a double cover, maybe you could explain so many different things. So what you're saying is E8 is special, but if we go up to 24 dimensions, the Leech might be even more tasty. That sounded weird. We're going to continue.
It may have been discovered by Witt about 25 years earlier, but exactly what Witt discovered is a little bit murky. The Leech Lattice turns out to be related to loads of other things. It became really famous when John Conway used it to construct various simple groups by looking at the symmetries of the Leech Lattice. It also turns out to be the...
Okay, so hold on. Let me just double check. Is that maybe that is actually the Leech Lattice? I mean, I don't have 24-dimensional vision. Let me just check because that looks very similar to the 120. So let me see. Did he just use the same thing? I mean, I wouldn't want to just be argumentative for the sake of being argumentative because that's basically what I do. But where are those little things? I just want to see. I'm not sharing. Oh, they added more stuff to this? Okay. Hold on. Let me stop this. Here's that. Construct and myself. Okay. I don't know. Maybe I'm just seeing things. Okay, maybe it's doing a little different thing. I feel like that's the graphic they're using. And this is the 120. So let me. Okay, see, you still see the pentagon there. Let's stop. Let's go back. I'm just calling it like I see it here. Again, I'm not a professional geometer or Fields Medal winner. Just a dude on the internet. That looks kind of like the same thing. It's okay. We'll go deep. We're getting into the fun stuff. Don't worry. Well, plenty of numerology ahead.
This possible packing of spheres in 24 dimensions. Marina Viazovska found an incredible method for proving that certain lattices are the densest possible ways to pack spheres. And what is really weird about her method is that it only works in 8 and 24 dimensions. It's really absolutely bizarre. The Leech Lattice also gives you things like what is the maximum number of spheres that can touch a given sphere. For instance, in 2 dimensions, it's pretty obvious that you can have 6 spheres touching a sphere and no more. In 24 dimensions, the maximum number is given by the Leech Lattice and is 196560. So how do you construct the Leech?
What is it? Okay, so the kissing number in 24 dimensions. Okay, so basically what they're talking about there is you have a central sphere. How many spheres could you pack around it? In this case, 1, 2, 3, 4, 5, 6. All right, that's cool. So what happens when you go to 24 dimensions?
Leech Lattice is 1965.
Like 196,560. Why? Because it is. So I mean, I don't know. You tell me. I'm just probably just trying to take note. Okay. Coincidentally, it's if you put a period there and you had it in like something gig electron volts. It's kind of close to the Planck energy, but no, it's different numbers.
60. So how do you construct the Leech Lattice? Well, the original construction by John Leech was very complicated, involves things like Golay codes and Steiner systems, which are very interesting, but the only problem with them is they're a little bit complicated to define and describe. Okay. And so instead what I'm going to do is I'm going to give an astonishingly short and simple construction of the Leech Lattice found by Conway and Sloan, which uses properties of Lorentzian space. So you remember in ordinary Euclidean space, we define the distance by taking the sum of squares of coordinates and taking the square root of that. So that gives you...
Wait a second. This is sounding surprisingly like physics. WTF, mate. Just some cool mathematical object, right? Euler.
The distance of a point from the origin. If you do special relativity, then you use a special Minkowski metric where you take x squared plus y squared plus z squared minus t squared. And you notice that there's this funny minus sign here, which makes everything very strange. So in particular, if you try and draw a picture of Lorentzian space, well, I'm going to sort of draw 3-dimensional space. You think of a 3-dimensional space here, there's an x-axis and a y-axis and a z-axis. If you take all the vectors of norm 0, this forms something called the light cone. So that tells you...
Wait a second. Why are our light cones popping in here? I'm sure it's totally irrelevant. I'm sure these are the reasons why math seems to be able to describe reality, but I don't know. Why is it that some fancy geometrical object is doing the standard thing that a lot of folks draw just when they go into a physics talk? Well, my friends, we may have a reason. We'll get into it after we finish this. Few minutes.
How light travels, and the vectors outside here are called space-like, and the vectors inside these cones are called time-like vectors. In Lorentzian space, you can still form lattices. For instance, you can take the lattice of all points x, y, z, and so on up to t, with all x, y, z, and t in the integers, say. So that would give you a sort of analog of the square lattice.
Wait. But the integers, you say? Well, it's not like some elementary minimal three manifold like the key-scheme manifolds. First homology group is the integers. We'll talk about that another day this week. There might be a little contest going on. We'll get into
lattice. I'm going to look at Lorentzian lattices in 26 dimensions.
Oh. We got the fancy
So this is called x0, x1 up to x24, and then we've got a time-like vector t. And the distance is going to be taking the square root of x0 squared plus x1 squared plus x24 squared minus t squared. Conway and Sloan took the following magical vector, 0, 1, 2, 3, up to 24, 70. And this is called a Weyl vector, drawn with that Greek letter rho. This vector has the following funny property. The inner
what is 70? Well, at least within a generalized Thad's model there. I mean, well, that's just basically two things of space because it has a number of 35 for its magnitude for the claimed amount of derangements and stuff. But that's it. Keep going, sir.
Product of rho with itself is equal to 0 squared plus 1 squared and so on, plus 24 squared minus 70 squared. And by some freaky coincidence, this is equal to 0. And 24 is the only number for which this holds, apart from trivial cases like 0 squared equals 0 squared and 0 squared plus 1 squared equals 1 squared. So apart from these two trivial cases, 24 is the only number for which the sum of the first n squares is a square. Now with this Weyl vector, we can now form a lattice as follows. We take the lattice of all points with all coordinates integers, which is called I25-1.
All right, so they say alternate integers, right?
With all coordinates integers, which is called I25-1.
Oh, no, that's a different word. I got my completely
and
wrong.
Inside this, we take the orthogonal complement of the vector rho.
Okay.
So this now has dimension 25. And now, because rho has inner product 0 with itself, rho is actually in the 25-dimensional lattice that's orthogonal to rho. If you're used to working in Euclidean space, this sounds kind of crazy, that if you take the orthogonal complement of a vector, the vector's not in that. But it can happen in Lorentzian space. So we can take this 25-dimensional lattice and just kill off all copies of rho. And this now has dimension 24, so we've got a 24-dimensional lattice. And this lattice here is not the Leech lattice.
All right. He's showing us all these little points and stuff, and our minds are going around. Look like there's some crazy tangled thing of DNA in there. All right. I remember watching this probably about a year or so ago with that. It's like, oh, that's a fantastical thing. It's like, I have no idea how the heck to get there from the stuff we were working on. I'm just like, actually, to be fair, I learned off, went on a road trip to visit a mad scientist with Casey. We were listening to Richard Borcherds. I think he was on Kurt Mungel's Theories of Everything podcast. Shout out to Kurt. And now going back, I'm like, all right, let me look up the Leech lattice. I'm like, hey, this video looks familiar. Oh, it is from Richard Borcherds. Cool. Let us continue, my friends.
It's very, very close to being the Leech lattice. Just take all the vectors x0, x1, x24, t, with the sum even. Here, you remember these are all integers, and I'm going to insist that the sum must be even. So that gets rid of half of it.
Wait. That's mod 2. Mod 2 for the integers. How very interesting. Maybe 2 is important.
And because the sum is either even or odd. And now we add in all the translates, a half, to make all its coordinates a half. So we sort of throw away half of it, then we double it up. And if you do this, then rho perp over rho is now the Leech lattice.
Please look back to the components of a subset of the Leech lattice. AKA, the thing is so ginormously ginormous. Okay. Again, I don't have 24-dimensional vision, but let's take a look. Oh, look at pretty. All this looks like the stuff you get out of Hubble and James Webb. Look again, we're pattern matching creatures, so we're looking
This
for
is
patterns.
particularly bizarre because the automorphism group of the Leech lattice is one of Conway's sporadic simple groups. Normally, sporadic simple groups are incredibly difficult to define explicitly. This is by far the simplest way of explicitly constructing a sporadic simple group that I know of. Incidentally, this trick of throwing away half the lattice and adding half of...
I don't know. I'm looking through this. I'm like, and we're going back into the matrix now. I'm sure there are people that can appreciate more than me, but what we're going to appreciate is why might this be the case? Because that's the whole purpose of this thing with the very lazy thumbnail that I just stole, that I done on Twitter and everything.
Something back else can also be used to construct the E8 lattice. So if we take the sum of 8 copies of Z and throw away half of it and add in the translates by this as before, we just get the E8 lattice in 8 dimensions.
Oh, is that all?
Okay, if you want to know more about this, the best place to find out is the book Sphere Packings, Lattices and Groups by Conway and Sloan, and you can find their construction of the Leech lattice in chapter 26.
I don't have that.
Let me just...
Unfortunately, I'm still working on an elementary analysis of area of calculus. So, okay. All right. So what actually is the Leech lattice, and why should we care about any of this stuff? Okay. Let's go to our friends over and go to the window now. Let's share with the class. All right. So don't need those integrals there. All right. So the Leech lattice. Mathematics. The Leech lattice is a unimodular lattice. What the heck is that thing? A unimodular lattice is an integral lattice of determinant 1 or -1 for a lattice of n-dimensional Euclidean space. This may be equivalent to requiring that the bond that a fundamental domain for the lattice be 1. All right, so there's a 1 thing going on. Cool. All right, and 24-dimensional Euclidean space, which is one of the best models for the kissing number problem. That whole thing with the spheres and the circles and everything like that. It was discovered by John Leech in 1967. It also may have been discovered, but not published by Ernst Witt in 1940. Okay, so he may have come across it. He just like, didn't actually put up for publishing, and it took 27 years for somebody else to find it and publish it. I'm just saying, this is probably why it's... If you want to share things with other folks, it might be useful, because it may take a while otherwise for folks to come around. Well, I don't know about that, Nolan. I don't know about that. I mean, those are some words. I mean, I could probably imagine something in my head. I don't know. All right. But okay. So the characterization, the Leech lattice, lambda 24. I believe that's how it says. Hold on, let me read. Okay, it is lambda 24. I feel good. I finally put in the dang plugin. All right, it's a unique lattice of 24-dimensional Euclidean space. E24, the following list of properties. It's unimodular. Okay, yeah, so that's 1 thing. And it can be generated by columns of a certain 24 by 24 matrix with determinant 1, because unimodular is 1 or -1. There has to be a magnitude of 1, I believe. If it is even, i.e. the square length of each vector in A24 is an even integer, the length of every non-zero vector in A of 24 is at least 2. Okay. This last condition is equivalent to the condition that unit balls center at the points of lambda 24 do not overlap. Each is tangent to 196,560 neighbors. That's a lot of sphere kissing going on, my friends. This can be known as the largest number of non-overlapping 24-dimensional unit balls that can simultaneously touch a single unit ball. That's a lot of words. It's the arrangement of a buttload of unit balls centered about each other. Another unit ball is so efficient there's no room to move any of the balls. Configuration together with its mirror image is the only 24-dimensional arrangement where 196,560 unit balls simultaneously touch each other. Property is also true in 1, 2, and 8 dimensions with 2, 6, and 240 unit balls, respectively, based on the integer lattice, hexagonal tiling, and E8 lattice, respectively. Oh, okay, and we're now here to the part that we actually came here for. It has no root system, and in fact is the first unimodular lattice with no roots, vectors of norm less than 4, and therefore has a central density of 1. So we got our oneness by multiplying this value by the volume of a unit ball in 24 dimensions. All right, so the volume of a unit ball in 24 dimensions is pi to the 12th divided by 12 factorial. It's very 12y in there. I mean, what? To be fair, this maybe should be expected, just because it's like, all right, anytime you're looking at an n-dimensional ball, you always get like a factor of pi to some factor of n or n minus this, that, depending on if you're doing volume, surface area, and a lot of times you'll have like a gamma or something down below them. But this, pi to the 12 divided by 12 factorial, one can derive its absolute density. Okay. So basically, when you go to Wolfram Alpha, let's do this. Let's go to the Leech Lattice, because you can just type it in. Oh, look, it's right there. Leech Lattice. What is this? All right. So description of lattice. So this is apparently its basis of stuff going on. Again, I don't necessarily know. It's this Graham matrix again. Fancy math stuff. Okay. So dimension 24, determinant 1, like we said there. A minimal squared norm 4. Stochastic number, blah, 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 blah. Okay, backing radius 1, covering rate. Oh, look, root 2 is there. And then the density of this, because that is 12 factorial. And then it gives you this number here. What is that? What is that number there? Okay. So if we do that thingy that we had, let's do that. Let's take our pi raised to the 12th. Okay. Oh, that gives us about a million-ish number. A little bit less. All right, what's 12 factorial? Oh, look, that ginormous number that we had over there before. Oh, 8th power. How very interesting. Okay, so what if we take that and we divide it by 12 factorial? What do we get? Look, I get, wait a second, this number looks kind of familiar. It looks kind of like, what was it, the Leech Lattice? Go back here. Oh, the density. Well, that's what Wikipedia had been saying there. We got a pi to the 12. We got 0.001929. What do we have? 0.001929. Wait a second. Okay, so we got that 47 not 16 not 47. Okay. 40 47 9 not 16 not. Okay, so it appears to be the exact same result. Okay. I don't have to tell you any of that. We already covered all that stuff from Wikipedia and everything. Okay. What is the significance of this? Okay. So Thad happened to find a closed form for this. So let's take a look. I got my friend right here. Okay. So we could say that's the row of Leech. The row of Leech. Hold on, let me bring it up. Oh, this guy. Boom. All right. So we've got row Leech. Okay, we'll do the density of the Leech lattice. What the heck is this? So coincidentally, you can break down or kind of break into different factors the pi to the 12th divided by the 12 factorial. I don't know. I got dodecahedrons on the brain, apparently. So we got this dude right here. What is this dude? So for those that have not been following, a red n is basically a 5. Basically, the 5 elements of our dimensions of measure, because basically within the constants of nature, you can break them down into 5 bases: time, space, charge, mass, and temperature. Again, don't hear a lot of folks talking about that. I feel that might be important. Okay. So what do we get? We got 4 pi. So we get a sphere, and we're dividing it by 5 factorial. So that gives us 120. Okay. Okay, that's not any of the Planck units, well, technically, but it's the factorial of 5. And if we take the subfactorial, or the number of derangements, the claim is that's the number of derangements of the Planck time, because it's of the 44th power. That's its magnitude. So we get a circle divided by 120. We got a circle divided by magnitude 44, the magnitude of the Planck time. We get a circle divided by 35, the magnitude of the Planck length. We get 4 pi divided by 18, the magnitude of the Planck charge squared. I get 4 pi divided by 32, the magnitude of the Planck temperature cubed. And we get 4 pi divided by 8, the magnitude of the Planck mass to the 4th power. Okay. Okay, I showed you a picture. I spoke some words. Okay, like we said earlier, trust but verify. How do we verify it? Well, we verify right here, my friends. All right, it's also in the doobly-doo, of course. Okay. Because we have this thingy here, so all we do is I go into Wolfram Alpha, I type that thingy, I set it equal to that crazy thing we were saying there. So you see, you get your 4 pi divided by your 5 factorial, the 4 pi divided by your 5 subfactorial. So that gives us 44, 35, 18, 32, and 8. Okay. We go to our Planck units. Okay. What do we have right here? The Planck length. That's magnitude is negative 35. Excuse me. So it's to the negative 35th power, so it adds a magnitude of 35. Okay. The Planck mass is magnitude of 8. Planck time is magnitude of 44. Planck time is magnitude of 32. And utilizing this form of the Planck charge, the magnitude is 18. So the 5 elemental bases of our dimensions of measure for the constants of nature happen to be right here. Oh yeah, it could be wrong. Well, at least according to Wolfram Alpha, it's not wrong. It seems to be true. These things seem to equal each other. Why? Oh, cut it out. Let's see what the heck happens. Oh wait, a pi over 12, 479, double lot 16, double lot. My friends, appears to be the same dang thing. Why? Now again, I cannot say. Welcome, Charlie. Oh, we're deep in the numerology today, my friend. All right. Well, this is the thing, because no way in God's green earth would I ever find something like this. Is it? Especially, listen, Leonard Euler figured out some of these things. What was it? Gauss apparently had like some hunch. It's like, it's what is it? X over log of X is that's obviously going to be what your standard curve and stuff like that. What? Listen, with tools like Wolfram Alpha, you just need to ask the proper question. If you can ask the proper question, and there's something relevant here, you can find answers. Uh, Basically, what we're going over is, if you look at these things here, so we have our Planck units over here. So Planck charge over here, just Q sub P, has a magnitude of 18 within this, because this is the standard one we use. You could use it in a different convention, but that kind of mucks things up, at least in my opinion. Again, I'm very biased. But so we have a magnitude of 18 there to the 18th power. So the magnitude of that, if you just do the absolute value, would be 18. And then Planck temperature will be 32. Absolute value of the Planck time is 44. Absolute value of the Planck mass is 8. Absolute value of the Planck length is 35. 8, 32, 18, 35. And that ends up being 44. Just because, don't trust me. Just We just check. Okay. So when it's first, it's called subfactorial, just because that's how we categorize it. If you use all exclamation point first, that's 44, and then if you put it out in the front, that would be the factor. So it'd be like 1 times 2 times 3 times 4 times 5. That gives us 120. 120 is also the number of vertices in the 600 cell, aka the hypericosahedron, which is an interesting thing. I'm not saying it explains all the stuff in the universe, but apparently this is an equivalent thing for the Leech Lattice. And again, is it more complicated than pi over 12 there? This is where math is like a superpower, just because, all right, what might this mean? All right, this is true. Now let's conjecture ahead, my friends. Why? Hold on. We got the little thingy here. We've got that.
You finally flipped.
Okay. We know that. We know that. But all right. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different
title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Roolead. I don't think it rules them all. And it might be just hyper-Ruleal turtles all the way down.
Yes, it's on the back of an infinite number of hyper-Ruleal turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey, Upcycle and Charlie, here's the thing. I'm a mortal dude. I got my fix earlier of all the random political stuff and people losing their minds about everything. People were celebrating. Other people were like trembling. I don't know. At this point, let freedom ring. Let freedom ring. That was inspirational. I did like the gentleman there, the pastor, I believe. But well, here's the thing. It's like I just got a call from Thad. He's like, I found something cool. And it's like, you gotta say, I'm like, oh, I'm driving right now. He tells it to me. I'm listening. I'm like, wait a second. Those numbers, and then eventually I stop and I look and I'm like, that's very interesting. So, all right. What you're saying is this crazy thing that apparently is the density of the Leech Lattice. So basically, by multiplying this value by the volume of the ball, basically pi to the 12th divided by 12 factorial, one can derive its absolute density. Okay, and that just happens to be equal to the number. And again, this is a way of looking at it, but if this magical 24-dimensional Leech Lattice has E8 built into it there, and E8 can do these magical things. And by magical, I mean it seems to be able to explain a lot of things within particle physics and stuff and things. And it just happens to be a mathematical object that we can discover because math is it invented? Is it discovered? Yes. I'm going to stand by that. But, okay, it's this thing here right here. But, okay, so let's break it into some parts. What the parts are we breaking into? All right. So if we get this guy, we got 44. So we got, all right, a sphere divided by 44 derangements of time, we're claiming. We get a sphere divided by 35 derangements of space, we're claiming. Or at least I can claim that. Then we got 4 pi over 18 derangements of charge. That's squared. Coincidentally, charge squared is very interesting within the model. Then we got a sphere divided by 32 derangements of temperature, and that's cubed. That is interesting because it seems like we live in the realm of temperature. Why? Because things can get hot. We can have a notion of temperature because we're on a scale. Because we're just a single atom, and you're just chilling by yourself. Do you really have a notion of temperature? I don't know. I think you need to be maybe in a larger. Some may say configuration space. I just like to think of it as our realm of persistence. And that's cubed. Kind of seems like we're in 3 dimensions of space. Again, I don't know. And then here's a very interesting thing. You get, and again, maybe this can be refactored in another way. I'm sure it can. When you get a sphere divided by 8 ranges of mass, I'll claim, let's raise to the 4th power. That sounds quite orthogonal. I mean, I can't really say much other than that. But the interesting thing is this 5 factorial here, we've got a sphere divided by 120. And I normally think when I hear 120, I think of 120 cell. However, and even though that may have been one of the images that Richard Borcherds may have gone from Wikipedia, I'm sure it was something different and not just, I don't know. What's the call, chat? Was it the same thing there? It looked kind of like the same thing a little bit earlier. I could be wrong, but ultimately that 120 cell, it has 120 cells. Maybe that's an interpretation. I mean, again, it is crazy that I just happened to, when you do the 70/81 thing, long story short, it leads you to something that kind of infers that maybe this, either the 120 cell or the 600 cell, might actually have something going on, and that would happen to be at the inversion boundary we claim, which is basically the absolute value or the Ampere constant, which is, you take the Ampere constant is basically you do Planck mass times Planck length, you divide it all by Planck charge. I need to put brackets on here. Nope. Wait. Yeah, okay. You can see here, all right, Planck mass times Planck length, all divided by charge. Oh, let me put my brackets on here, it makes me feel better. Feels more organized in my head. Okay. The Planck mass divided by the Planck length over Planck charge squared is this, looks like 10 to the negative 7. Might have some disagreement with that. But essentially, that is 1 Ampere constant. Okay. Well, this is a cool little thing. Very interesting things happen here. So, like for instance, if you were to multiply, let me just do this c squared. Okay, well that's interesting. But if we just multiply it by c, the speed of light, you get this volts per ampere, ohms. Coincidentally, that's I believe that's the Planck impedance. I forgot about that in the video before. Could be. Oh God, there's so many terms now in Wolfram Alpha. It's 1,200 Wheatstones. How does that even make any sense? One of the physics things I got before was like crabs or something like that. There we go. Okay, after like 40 something terms, we find that that is 1 Planck electric impedance. So it's an interesting thing because all you literally got to do is just add speed of light, and by add I mean multiply. One of those things right there. But what is it? It's well. Here's the thing, Charlie. I tend to think politics can be. I originally started out kind of in the political sphere and stuff, and I realized a lot of people just don't seem to like each other and just seem to want to fight because it's profitable. So then I kind of like checked out and kind of like went into science because I'm like, okay, maybe we can actually like, rather than just be like, you're bad, you're evil, you're no good, very bad, blah, 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 this, that, the other thing. Rather than calling people names, maybe we could just argue about like ideas and stuff because that was the attraction. I like talking and arguing about ideas and everything, but I feel like you can come at it from a good-natured position. The problem is that usually doesn't get a lot of views. What do people like? They love seeing the stones that destroys. They love the ultimate dumpster fire as long as it's not your dumpster. I'll talk about it sometimes, but right now this channel is mostly geared towards the scientific stuff. And then on Thursdays we play with Fizz because wolf girls are fun. Sound a little wrong. Okay, here's the thing, Charlie. From the experimental side of things, there's actually very fantastic stuff happening. Like some of the ICTS's videos, they'll do like lectures usually while I'm kind of like getting ready to go to sleep, and I'll pop in there. And occasionally I'll see somebody is like, we have a 20 to 30x magnitude, like, or like 20 to 30 times output greater than we expected. I go back the next day to check the lecture. I'm like, oh, that got pulled down for a reason. I wonder if that guy got a wonderful government contract. Hey, power to him. But there's a lot of people doing a lot of great things. It's just, you don't always hear about it because, oh, well, I don't know, Royal Academy of Sweden isn't really talking about it, or it's not on one of the larger channels and stuff, whether it's Dr. Tyson or Dr. Green or something like that. It's like people only have so much time. They talk about things that interest them. But it's our job to keep track of the little gems because there's a lot of BS out there. But every once in a while, you can find a real small gem. And if it explains a lot, because my big thing is, at least with this, it's like, okay, this is cool right now. This is just numerology. Now, numerology is numerology until it explains more with less. This just happens to be for the density of the Leech Lattice. It's very interesting that these things pop up. But what can we do from it? I don't know. Because right now we're kind of trying to map out. We're like, all right, we got 5 bases. We got 5, kind of like the Platonic solids. We have some higher dimensional shapes, whether it's the 600 cell or the 120 cell or something. Those are 4-dimensional Platonic solids. Technically, there's 6 of them in 4 dimensions. So it's very interesting about these fantastical geometries and where they may actually come into play. Let's see. It's I try to a lot of times I'll pop on there for they usually do the Patreon meeting usually like 1 p.m. East Coast time, 10 a.m. West Coast time in the States. Usually after that, that goes for an hour. So usually like around 2 p.m. East Coast, 11 a.m. West Coast time. I'll usually pop in there for like an hour and just chat with whoever's around. It's hey, no. It means a lot, man. It means a lot. It's just getting people interested in things, and you never know where a good idea comes from. I talk to folks, I interview different people and everything. It's like I've had folks from like Stephen Wolfram, Jonathan Garrod, and occasionally a couple of crazy people here and there. But just try to treat people with respect, try to be friendly, just go after somebody to go after somebody. You can have some fun, have some dignity and respect. Hey, what's going on, Alchemist? How you doing, my friend? What's going on? No, long story short is what was it? Okay. So the quick talking points, because we're getting towards the end here, is all right, you go to the Leech Lattice. Apparently its density can be calculated by this right here. Okay. So pi to the 12th divided by 12 factorial. Okay. To get its absolute density. Okay, so that's cool. What's it give us? Gives us this crazy number right here and everything. So by the 12th over 479, not 16, not. Okay. That had found that if you can actually decompose that pi to the 12th divided by 12 factorial into these components here. Now, the interesting thing about these components, and there is an additional term in there, keep in mind, is if we go to our friend the Planck Units, and again, maybe this might just be nothing, but one of the reasons I'm talking about is because, one, I'm biased, because it does help bolster Thad's claim that the magnitude of the exponents of the Planck constants, there's something going on there. So that's the reason. So let's just go now. Okay. So we have Planck charge over here. We're going with this convention over here because, well, it's also on Wolfram Alpha and it's generally accepted. But basically, it has a magnitude of, it's at minus 18, 10 to the minus 18. So it has an absolute magnitude of 18. And when we go to our other friends, we see the Planck temperature. It's got a magnitude of 32. Planck time has a magnitude of 44. Planck mass has a magnitude of 8. Planck length has a magnitude of 35. And if we notice here, it's like, wait a second. Magnitude of 8, like the Planck mass. Magnitude of 32, like the Planck temperature. Magnitude of 18 for the Planck charge. Magnitude of 35 for Planck length. And then that's 5 subfactorial, and then that's just 5 is 44. So that's the magnitude of the Planck time. And then we have do it after 5 factorial. Excuse me, that was subfactorial. This is 5 factorial. That's 120. I misspoke. Pardon. Okay. So, and again, this is just an interesting thing. It's like, wait a second. This fancy lattice and everything, you just kind of break it apart into its factors. It's like, all right. So what could I say about this? 120? I don't know. My mind goes to something like the 120 cell, which is the 4-dimensional platonic solid of the dodecahedron. Or perhaps it's the 120 vertices of the 600 cell, the 4-dimensional platonic solid of the icosahedron, the hypericosahedron. I mean, wouldn't that just beat all? If all of a sudden it's like back in the days of ancient Greece, a lot of like they discovered the platonic solids. Well, obviously, our world must be created of these things: earth, wind, air, fire, water, ether. Totally no ether. But I'm just saying, wouldn't it just beat all if they were just off by 1 dimension? If they literally just needed to conceptualize 4-dimensional geometry and we live in some 4-dimensional platonic solid, I think that would be pretty neat. Maybe that's poetic justice again. I don't have any evidence aside from the occasional calculation where it's like, oh, that's kind of interesting. Can't just plug it in and be like, oh, here's the code to reality. Maybe it does exist somewhere. I don't know. Where are we at? Let's see. All right. So I think we can start winding down here. Yeah, there's a lot of cool stuff there. Let's just go into a couple. Do we have anything else? Let's just look a little bit more at the Leech Lattice because they use it for apparently it helped our Voyager probes. Oh, because remember Richard Borcherds when we were watching his video on how to basically create the Leech Lattice. He started talking about the Golgi groups or code or whatever, and then the other ways they had kind of gone through them. He's like, it is very complicated, and it's like, we're not going to do that. We're just going to start with doing this, and he showed the pretty pictures and everything. But apparently, yeah, because they were using. Let's just read it. The binary Golgi code. What the heck is that? Okay. In mathematics and electronics engineering, binary Golgi code is a type of linear error correcting code used in digital communications. The binary Golgi code used along with the ternary Golgi code. Oh, it's been a while. The particular deep and interesting connection to the finite of the theory, the connection of the theory of finite sporadic groups. Okay. Coding theory. All right. So basically, it's an error correcting code, correcting up to 3 errors in each, and I think it picks out 4 and detecting up to 4. Okay. So it's a very rigid code that apparently is good at error correcting. Okay. Let's see. I should probably I skipped over so many of these different things. Quantizer or analog to digital converters can use lattices to minimize the average root mean square error. Wow. I usually just see that on Wolfram Alpha. I should probably actually look into that. I feel like that's very important, especially if we want to build things. Most quantizers are based on the 1-dimensional integer lattice, okay, but using multi-dimensional lattices reduces the RMS error. Oh, Leech Lattice is a good solution to this problem, as the Voronoi cells. Is this coloring things, partial and plane, each of the given sets of objects be classified as a tessellation in simplest case, the opposite just finite and many points on the plane. Okay. Have a low second moment. Okay. Vertex algebra, the 2-dimensional conformal theory describing bosonic string theory, compactified on the 24-dimensional quotient torus R24 divided by lambda 24 is our Leech Lattice. An orbital folded by two element reflection group provides an explicit construction of the Grice algebra, the commutative non-associative algebra on a real vector space of dimension. Oh, that seems to be a little higher than dimension 196,884 that has the monster group M as its automorphism. Oh my god, are we literally finding monsters? That would be neat. As a monster group, this monster vertex algebra was also used to prove the monstrous moonshine conjecture. That's what Richard Borcherds did. He proved the monstrous moonshine conjecture. I remember now. Blah, blah, blah. It's made. Okay. It was proven by Richard Borcherds. The moonshine. Okay. The no-cost theorem from string theory of the vertex. Okay. Yeah, there's a lot of stuff there that I do not know. I just remember listening to a couple of his interviews on Mr. Jen Mungel's channel. Very fascinating. Very nice guy to listen to. I like how it's like, what are your secrets? It's like, well, I get up late, I procrastinate a lot, and then I do some stuff. I'm like, oh my god, are you my spirit animal, Richard Borcherds? I don't know. I'm like, I feel like I resemble that. But what are we gonna do tomorrow? Let's give folks a little sneak peek. Okay. So what we're gonna do tomorrow until I get a different idea is let's go over here. When you spend enough time going down a Wolfram hole, eventually you notice some things. Like you might notice, I don't know, it's like temperature. It's ginormous number here. Okay. And then maybe you notice something else. Maybe you know something like H bar. We have a really ginormous number. Oh, we have a redonkulously small number. I'm sure nobody knows where I'm going with this. What happens if I type in both those magic words? We want to use it as a unit Wolfram alpha. Okay. We get this crazy thing right here. And again, we could divide the units out and everything. But this is a very interesting number. Why am I showing you this not 0.0149441 yada yada? Okay. So just because I spent far too much time on this, if you use a certain geometric object, perhaps let's say Gaussian's constant, gives you a decimal. Wait a second. Some of these digits look off, but it's not quite. Why? -1. Wait a second. 0.04. Excuse me. 0.014941. Wait a second. That sounded a little familiar. Well, let's duplicate this. Okay, we'll go back. Wait a second. 0.014941. 0.014941. My friends, why does this look like the Gaussian constant -1? This is the Planck temperature, and this is the reduced Planck constant. The maximum bound of temperature in our reality times the minimal unit of action in reality. WTF, mate? Now, again, what the heck this means, this is in some incoherent dimensions. I mean, I could just divide the, let's just do that right now. By Kelvin, then divide by joule second, then divide by temperature, divide by energy. Oh, got that number. Okay. What? Huh. It seems to get all those did. 1, 2, 3, 4, 5, 6. And it goes for 7 digits. How about that? Well, Newtonian gravity seems to work for about 7 significant digits. We get about 7 significant digits of the Planck numbers of our Planck units. Huh. I wonder if something interesting is going on there. To be fair, we're going to claim that we need at least 14 significant digits because that's like the most number of significant digits that's on code data right now. This anomalous moment of the electron. There we go. That's got 14 significant digits. Dang, that's a hard one to get. We still might need to work on it, but I just find it interesting that if you take, we just take the maximum temperature and we multiply it by the minimal action, we get -1 of the minimal 3 manifold. Now again, that's just some numerology right there. I'm gonna need to have to find the second piece, and I'm gonna see if maybe somebody wants to help me with that tomorrow. But that's gonna be the plan for what we got going on. Other than that, hey, it's a new day, new stuff and things going on, and hopefully all are well. So other than that, hey, peace out, everybody. Take care of yourselves. It's a wacky world out there, but let's hope for the best. Catch you all next time.